Hi everyone, Mr. Boltri here, coming to you with our first AP Physics C video, and we're going to run and analyze the Buggy Lab. So I know we talked together today in class, but I just wanted to say hello again and say that I'm excited to be your AP Physics C teacher. And also I wanted to emphasize that we're going to cover a lot of material in this video and in the beginning of this course, because a lot of it should be a refresher, a reminder of what you learned freshman year. And if we're ever going too fast, we've dedicated the time in class to talk and to ask questions and to slow down. But just in this video, I wanted to cover more content so that we would be able to use our valuable time together to answer questions. So we're going to run the Buggy Lab, which you might remember from your freshman year. It's pretty simple. The purpose is just to take a little buggy and look at the relationship between the position and as time goes on, just the position and time. So in this class, we're going to use the symbol X to represent position because it's the position in the X direction. This whole unit, we're going to focus on one-dimensional motion. Actually, we're going to start by focusing on one-dimensional motion and then expand to two- and three-dimensional motion. So when something's moving in the Y direction, we'll call it Y, and something is moving at you or away from you, we'll call it Z. So first, I wanted to show you just a little video where you can see what the buggy is and what it does. It's kind of just this regular old buggy. You kind of put it on the table and it scoots along. Nothing really special to it. And this buggy in particular, the blue one, is pretty slow. So it just kind of drives along its little happy way. And here's what we're going to do. So I just thought it'd be more interesting if we ran two at the same time. So we're going to have the blue one starting in the negative position region and the red one starting in the positive position region. The blue one's going to move in the positive direction and the red one is going to move in the negative direction. And we're going to see what happens. Before we get started, we probably want to set up our data table. So we have the time at 0 seconds, 1 second, 2, 3, 4, we're going to record the position of the red buggy and the blue buggy. Normally, I'd like more data points than this, but my desk isn't very big, so we're going to have to settle with 5, which for the purposes of what we need to do today is fine. So Mr. Santee nicely volunteered to help me run this lab, and I'm going to show that to you now. So I'm sort of going to do a 3, 2, 1 countdown, and then we're going to place these little markers every 1 second, 2 second, 3 second, and 4 second, just so those markers will remind us what was the location of the buggy at those different times. So just by looking at it, you can see that the red buggy covered more distance than the blue buggy in those 4 seconds. And the data actually looks like this. So you can see at 0 seconds, the position of the red buggy was 80 centimeters, the position of the blue buggy was negative 20 centimeters, and on from there. So then the question becomes, what do we do with this? And I hope at this point in your high school science career, your first instinct is, well, we should probably graph it. So I'd make my freshmen draw everything out by hand and do the appropriately labeled axes and check their scales. But I'm really hoping that you guys are experts at that by now. So I'll just graph it for you and we see what it looks like. So we can learn a lot just by looking at this graph. Looks like and we could also have learned a lot by looking at the data table too, but in graph form, it's a lot easier to see. And one of the things that I hope you recognize is that both data sets seem to be pretty linear. So it would be appropriate for us to draw a line of best fit on both. And then we can just double check by making sure the line of best fit seems to match the data. And I would say that yes, it does seem to match the data. So we can see that the red graph has a negative slope, and the slope seems to be much steeper than the blue graph, which has a positive shallow slope. And that's going to be important later when we start talking about what is the meaning of the different slopes of these graphs. Also, something that should be pretty obvious is the red graph has a vertical intercept, which is in the positive region, and the blue graph has a vertical intercept, which is in the negative region. So before we dive too deep into this, I just wanted to review just a tiny bit of vocab of the difference between position, displacement, and distance. So position is just where something is at a given time. So for example, at 0 seconds, the buggy was at a position of 80 centimeters. Displacement is how far something is from where it started. So at 0 seconds, it is 0 centimeters away from where it started. It is where it started. But then as time goes on, it moves farther and farther to the left of where it started. And then distance is just the total distance you travel. So at 0 seconds, it had traveled 0 distance. And then from then on, it travels more and more distance. So if you're the kind of person who likes to write down definitions, that sort of stuff, this is kind of the most basic definition. But the biggest thing to remember here is that displacement is a vector. So if something moves to the left, it is now to the left of where it started. But distance is a scalar. So it's like a Fitbit or the odometer on your car. It doesn't care if you're moving left or right or north or south. It just is keeping track of the total distance traveled. And now we get to the really fun part, is we get to analyze the graphs of motion that we were looking at earlier. So when we start to analyze graphs, we look at mostly 3 big things. We look at the vertical intercept, we look at the slope, and we look at the area. So when we look at the vertical intercept for this graph, we notice that it intersects the vertical or y-axis at 80 centimeters. And if you remember from the experiment, the red buggy actually started at 80 centimeters. So we can say that the vertical intercept is the initial position of the car, which I hope makes sense because that is just the position of the car at time 0 seconds. So not too complicated, hopefully straightforward. Now slope is where things start to get a little bit more interesting. Remember, slope is rise over run, change in y over change in x. So for this graph, it's going to be change in position over change in time. The units might be something like change in position, centimeters, divided by change in time, seconds. Centimeters per second is going to be something like a velocity, which is just defined as how much the position changes per unit of time. So per 1 second, the position changes by negative 42 centimeters per second. That's just what the velocity, that's how the velocity is defined. So the area for this graph, I'm just going to say before I show you, is not something that we need to know for this course. It is something that only physicists who work with like fluid dynamics and some fluid engineers use. But I did want to talk about area for this graph, not because you need to know what it means, but to review that when we talk about the area for graphs, we really mean the area bounded by the horizontal axis and the function on a given time interval. So on this time interval between 0 and 4 seconds, the area between the function, the red line, and the horizontal axis makes these 2 triangle shapes. And if you're interested in Googling it or anything, it's technically called absciment. But like I said, we don't need to know it, and you probably won't need to use it unless you become a fluid engineer. So we have our XT graph, or our position versus time graph. And then on the AP exam, you're going to be asked to translate between the different graphs. So given an XT graph, what would the VT graph, or velocity versus time graph, look like? So like we said before, the velocity is the slope of a position versus time graph. So we can calculate the slope of our XT graph. And again, hopefully your math abilities are strong enough to recognize that that has a constant slope. So if we calculate the slope using any 2 points, we are going to get the same value, negative 42 centimeters per second. So if we graph just a whole bunch of negative 42s at all the different times, we get a velocity versus time graph that looks something like this. It's negative 42 centimeters per second for the whole time, because the car is moving with a constant velocity. And now that we have this velocity versus time graph, we can analyze it too. So some pretty simple things are the vertical intercept. Much like the position versus time graph, the vertical intercept tells us what is the velocity when time is 0 seconds. So we're just going to call that the initial velocity. Pretty straightforward. Now slope is where things start to get a little bit interesting, except for this graph, the slope, if we were to calculate it, would be 0, which means that the rise, the velocity, is not changing at all as time is progressing. So that would be 0 centimeters per second every second. And we just use the word acceleration to describe how much the velocity changes per unit time. And the units of acceleration could be centimeters per second each second, or centimeters per second squared. Either are totally acceptable. The reason why typically I prefer centimeters per second each second instead of centimeters per second squared is because that retains the meaning of a velocity on top, centimeters per second, over a time on bottom, seconds. Now, I know centimeters per second squared is a lot easier to say, and it's a lot easier to write. So you're totally welcome to say and write that. Just sometimes I might say centimeters per second each second, and I want you to know what I mean. And last but not least, the area of this graph makes a pretty familiar shape, just a nice little rectangle, but I don't want to give it away as to what is the meaning of the area. Now, you might remember from freshman year if you have a really good memory, but hopefully you can just sit here and think about it. You might have to actually look at the units and figure it out. So just again, if this is the kind of thing that you'd like to write down, I would suggest it. Velocity is just the rate of change in position with respect to time, which we can find as finding the slope of a position versus time graph. And acceleration is the rate of change in velocity with respect to time, aka the slope of a VT graph. So kind of last thing I want to do today is we know that the slope of a VT graph gives us the acceleration, and the slope of this velocity versus time graph is 0 for the whole time. So if we wanted to make the acceleration versus time, or AT graph, it would just be a whole bunch of zeros for the whole time. And moving forward, we're going to start to use acceleration versus time graphs that have non-zero acceleration and even changing acceleration. And that's when things get to be a lot more interesting and a lot more fun. But we kind of had to remember all the stuff that we learned freshman year first in order to do those more interesting and difficult problems. So this was kind of just a refresher, a little bit long, but of the basics of kind of kinematics and looking at position versus time, velocity versus time, and acceleration versus time graphs. This has been Mr. Boltri giving you video 1.1. Remember, if you have any questions, we have a dedicated class time tomorrow to ask those questions. So make sure you write them down, and we will make time to answer all of the questions, including making sure that everyone is confident on what is the meaning of the area of a velocity versus time graph. Thanks for listening. Be well out there, and go Bears.